So on the one hand, wildfires kind of actively contribute to climate change. So globally speaking, they're responsible for approximately 10% of all carbon emissions. And this kind of already leads us to the second problem, that global warming is leading to a lot drier conditions in a lot of regions worldwide. And these conditions lead to unpredictable wildfire behavior, and especially to a lot of unusually large wildfires, and then kind of rinse and repeat, and the circle starts again. So as you can see, there's really a large incentive for developing models that can successfully predict wildfires. So for example, so that you can be able to evacuate people in time, or to make informed decisions about where to station firefighters, for example. And there is actually a lot of research going on in wildfire prediction. So there's two large groups of models. On the one hand, there's physical models and also machine learning. So physical models tend to produce pretty good results, but there's a lot of domain knowledge required. So you need to explicitly model the physical and environmental conditions that lead to wildfires. And they also tend to be very compute intensive. Machine learning models, on the other hand, are relatively lightweight. And another advantage of them is that they are data-driven and descriptive rather than prescriptive, so they can learn from the data the conditions that led to wildfire. And this is especially important because climate change is kind of changing a lot of the notions that we had about which processes cause wildfires. However, there is a drawback that machine learning models tend to be quite complex black box models, and we do not know why they make their predictions in the way they do. But we still see that machine learning is kind of the way to go. And our sponsors from the National Observatory of Athens are really quite pioneering the way for predicting wildfires with deep learning. And this is also why we decided to reuse some of their work. They developed some really good models and that can successfully predict wildfires. And we then started to employ some explainable AI methods on those models. And for those of you that ask themselves, what does explainable AI do? So the answer is, well, it's quite complicated, but to put it simple, it's kind of finding explanations as to why a model makes its decision in the way it does. So there's actually a lot of research going on in explainable AI, but it is mostly done for classification cases. So for example, if you have a picture and you want to determine what is in the picture, you could say, okay, this is a cat, and the reason why it is a cat is that it has a tail and pointy ears and a fuzzy coat or whatever. But our use case is a little bit different. It's called segmentation. So we don't want to predict what is in the picture, so we want to see where the thing is in the picture. So in this example here, it's where is the cat? But for us, it would be where will the wildfires happen? Okay, so how can these explanations look like? And for that, I brought one example. They're called Shapley values. It doesn't matter too much what they are, but they are pretty much a rating of how much each input feature contributed to a prediction. And in this plot here on the x-axis, you can see the feature values for total precipitation. So the further on the left, the lower the value. And on the y-axis, you can see how these values contributed to a wildfire prediction. And as you can see, low precipitation, so dry conditions, kind of increase the prediction towards fire. And then very humid conditions have the exact opposite effect. So when it rains a lot, the risk for wildfires go down. So how did we get to these findings? So We started out by exploring the data set that we got from our sponsor. So it is a quite complex data set that has a lot of data on features that could potentially influence wildfire behavior, so precipitation, temperature, surface pressure, and so on. And also the burned area in each region worldwide. Next, what we did is explore a little bit in what different algorithms and Python packages and everything were available. And we soon found out that there's not a lot of explainable AI for semantic segmentation. As I said, we try to find kind of where a wildfire will happen. So for each pixel, we have a prediction that's will burn or not. So there will also be explanations for each pixel. So we thought it would be a good idea to aggregate the explanations, but this turned out to be a little bit complicated. So we thought maybe what we're doing is the wrong thing. So for a little while, we switched from merely predicting whether there would be a wildfire to predicting the size of the wildfire that would happen. And the results of how well or not well it could predict were actually quite good, but we still had the problem that aggregating the explanations proved kind of difficult. So we decided to kind of go back to the roots and do explanations for smaller regions. And what we ended up doing is developing a dashboard for visualization for those explanations. And so this is what it looks like. Maybe I have to step over a little bit. So here is, maybe not. So here you can see the dashboard. There's a region in Eastern Europe. You can see where wildfires are happening. And then you can you still hear me? Yeah. You can choose the explanation algorithm you want and the window size you want. And it's kind of interactive and customizable. And then for each of the input features, so for example, relative humidity, sea surface temperature, and so on, you can get the contributions. So obviously, this is still some sort of work in progress, but we do hope that there will be some more work on this project so that it can really do, maybe some good in the world. So these are the main packages that we use, Captum and Shap. They're both Python packages. If anybody's interested in working on explainability, it's really a hot topic right now. There's a ton of tutorials online, but also if you have questions, feel free to approach me afterwards. And last but not least, this is the team. So Giovanni is unfortunately not here today, but I do think he is dialed in via Zoom. And we had Cristiano as our coach and also Michele as our mentor. He is a postdoc, I believe, at the University of Valencia. And last but not least, we also want to really extend a special thank you to the research team from the National Observatory of Athens. So this is us last week, where we met at a geosciences conference, where Johannes also presented the SeasFire project. And we really want to say thank you for their guidance and help and advice. And that's it from my side.